Hey everyone, today we're going to be talking about a concept that is well researched and used commonly in today's technology, and that is the neural network. So, the neural network is a common idea in artificial intelligence and machine learning, in that what the neural network can do is you can train it. Essentially, you give it an input, observe the output, tell the neural network how far that output is from the desired output for that specific input. And eventually, the neural network will get so good that if you give it any input, it will give you the desired output that it wants. So for example, in handwritten digit recognition, you might give it a 28 by 28 image, or like just some sort of pixel image that shows some handwritten digit 2, like this. And the neural network will be able to recognize this as a 2. So that's the idea of neural networks. And of course, they do it to some degree of accuracy. Now, if you actually Googled an image of a neural network right now, you would probably see a very daunting image of just tons of circles, tons of lines. It looks like an entire spider web, and it gets pretty intimidating. So for this example I have on the board, we're going to use a very simple neural network, just to illustrate what actually happens. So, for this part, we're going to be focusing on feed-forwarding data. So we're going to have an input, and we're just going to observe what the output is. So for this example, the input layer is basically a series of factors that you are going to consider, and the output layer is the final decision. So our scenario is that there's a concert going on. There's a concert coming soon, and it's an artist you really like. So 3 factors you might want to consider are the location. So is it too far? And this will be our first sort of neuron up here. And then this second neuron is going to refer to too expensive, or how expensive tickets are. And then this third one is going to be our friends going to this concert with me. So these neurons basically represent certain values in the neural network, and sort of these input values will correspond to a certain output value. So how does that actually work? How do we get from an input value to an output value? Well, it involves the activations that are associated with it. So the activations associated with each individual neuron, they can be typically in the input layer. They are values between 0 and 1, and they're usually just 0 or 1, indicating that 1 is sort of on, 0 is off. So essentially, we're going to use these input values, and then we're going to use these connectors. And these connectors have something called weights associated with them, which I'm going to get into later. And you can sort of use some mathematical algorithm to utilize the weights and the activations to compute the activations for the output layers. So the notation here I have for the activations is that the subscript represents the individual neuron, and the superscript represents the layer that it's pointing to. So in this case, we have a 2 in the superscript. It's not a squared, it's just the activation in the second layer for the first neuron. So back on the topic of weights here. So each individual connector that we can see has a weight associated with it. And these weights, pretty much you can think of them as how much does the activation of this neuron influence the resulting activation outputs. So the way we would notate this is we would have the weight for this layer, and we would have the weight for, for layer 2, because it's going from layer 1 to layer 2 of the neural network. And this is going from the first neuron of the first layer to the first neuron of the second layer. And likewise, what we might do here is we're going to do W2, and then we're going to call this 2, 1. And I know I was kind of backwards for the notation I did originally, but the way I want to do this is that it's going to the second neuron from the first neuron. That's the way I want to do this. So, and likewise, we're just going to repeat the process for all the other connectors. So we're going to get something that looks a little bit like this. And now, what can we do with these values? How can we get these weights, and then we can somehow get some sort of activation out of this? Well, it comes with a little bit of matrix multiplication here. So the activation vector for this first input layer can be represented as a three-dimensional vector here, or a vector with three components. And each of these components are just going to be the activations for each neuron, right, in that layer. And the activation layer for the second one, or the activation vector for the second layer, for the output, is going to be a 2x1 matrix, or a 2x1 vector. And this is going to give you, and the components of this vector are just going to be the activations for either neuron. So how are we going to get from a three-dimensional vector to a two-dimensional vector? Well, we need to use a matrix, more specifically a weight matrix. So the weight matrix for this layer, for the output layer, is going to be a 2-row, 3-column matrix. And this matrix is just going to store the values of all of these weights. So it's going to look something like this. We'll have weight 1, 1, weight 1, 2, and then the weight for 1, 3. And then for our second neuron, it's going to be weight 2, 1, weight 2, 2, and weight 3, 2, 3. Just like that. And that way we will get this two-dimensional vector here. But what if we wanted to focus on each individual neuron here? Well, that's pretty simple. We can get a sort of weighted sum by looking at all the neurons that feed into, by looking into all the connectors, or the weights that feed into this output neuron here. So let's take a look at this activation here. So we're going to go ahead and put a function here. So this function is just going to be so that the value for this activation is between 0 and 1, because that's what we want for this activation in this case. So it's going to be the function of some weighted value for the first neuron in the second layer. And how do we get this? Well, this is just by multiplying each neuron activation for the input layer by the respective weight. So what that's going to look like is that's going to be A11 times this weight right here, W211, plus this A21, and then this corresponding connector, and then plus A31 plus W213, or plus W213 times A13. And I'll go ahead and to keep notation consistent here, we will go ahead and use this. And now what we need to do is we need to go ahead and throw in one last term here, a bias. And this bias pretty much just says how much, the bias is pretty much just a sort of initial value you can kind of think of. It's sort of just an extra value that you need to take into account, and that value is associated with the individual neurons. So there's going to be a bias vector at play. And that bias vector is going to have the exact same dimensions as the output activation vector. So it's also going to have pretty similar components. It's just going to be the bias for each individual neuron. So in our case here, we're going to use the bias for the second neuron, or the first neuron in the second layer. And now what can we do with this? Well, we need to sort of determine what this function is going to be. So a common function used in machine learning is what's called the sigmoid function. So the sigmoid function we can describe as sigmoid of z, which is a logistic function. It's sort of the base logistic function you can think of. It's 1 over 1 plus e to the negative z. That is our logistic function. It is our base logistic function. And what's nice about this sigmoid function is that we have our 0 here, and it looks something like this. And so it asymptotes to both 0 and 1. And that means that this sigmoid function acts as a sort of squishifier, and that it takes this weighted sum here and then translates it to 1, or to some value between 0 and 1. So we can say that A12 is going to be the sigmoid of this weighted sum right here plus a bias. And to compact this a little bit more, we're going to go ahead and put it into sigma notation. So this is going to be the sum from some value k of A, referring to the previous layer, AL minus 1 k times W of the certain layer that we're looking for. And this is going to be J times K, J of JK, meaning that it's the jth row, kth column. And it's going to be just this summation right here plus B in some jth layer of the, and for some jth neuron of the lth layer. So, and this is actually just the general notation for an activation. And that's it. This is how we can use these input neurons here, throw them into some weights, think of them as, again, you can think of them as how much you prioritize each decision, or how much you prioritize each factor. So to put it into an example, because I believe I haven't done that as of yet. For example, let's say it's too far. The location is super far, and you just cannot go to a concert that's super far away. So what you might do is you might make these weights slightly larger in magnitude compared to the other two weights. So you might have something like, so you might have the absolute value of this weight being like 6, and then the absolute value of this weight being 2, and of course absolute value of this being like 1, for example. You might just have that, for instance. And so that's what a weight kind of represents. So you can store these weights into a weight matrix and then multiply that weight matrix by the input activation vector, and you'll be able to get an output activation vector with components referring to the activations of either neuron in this case. So we can put that in compact notation as well. So this is the activation vector for some layer. This is going to be the weight matrix for that particular layer times the activation vector for the previous layer plus the bias vector for the new layer. And these two equations right here make up the idea of the feed forward. So, sorry, wait, this is not what we want here. We want to put a sigmoid around this because this right here, this value right here is referring to weighted sums again. So let me just recap again. So this matrix multiplication is going to result in a couple of weighted sums. And these weighted sums are going to refer to the weighted sums referring to either of these two neurons. So there's going to be a weighted sum for this neuron and a weighted sum for this neuron. And then we just throw that into a sigmoid function. And that sigmoid function outputs a value between 0 and 1. And that will be our activation. So we can now observe what this value is, what the activation values are going to be after we throw in that input. And 99% of the time, or not really, almost 100% of the time, these two values that we get are going to be completely off from the values that we want. Hence, we want to find something called the cost of this neural network, or the cost of this input, and that's where we'll pick up next time.